Hey everybody, we're going to talk about this law right here, Gay-Lussac's law, and I've got all three targets on here, or target 2, 3, and 4, because given the situation where I'm gone, I think it would be best to take a gas law and just apply all three targets to it in one video, and then switch to the next video and do the next gas law. All right, so that might cause a little bit of confusion when you're taking your notes, so you can take your notes the best way you can. Maybe in your own notebook, following my videos, and just leave the notes blank in your packet. You still need to do the applying section in the problem set, but I think this will work. And the gas law I want to talk about, Gay-Lussac's law, it relates temperature versus pressure at constant volume. All right, so constant volume. And if you were to, let's say you took a jar and room temperature, glass jar, got room temperature air in it, put the lid on, and let's say we take that jar, it's sealed, and we stick it in some room temperature water, and then we start heating the water. And if we had a magic pressure sensor inside the jar that would wirelessly send us pressure data, and we had a thermometer to measure the temperature. Well, what you would see as you gather data would be what the graph, something like what the graph shows. I mean, the graph is showing pretend data, but it would be about right. What you would see, okay, so let's say we are changing the temperature. We choose the temperature values. That's the independent variable, and the independent variable goes on the horizontal. Pressure depends on what nature does. And so it's on the vertical. Now, let's say we took some room temperature air and put it in room temperature water. Room temperature is about 25 degrees Celsius. And then we began heating it up because it's sitting in water that's heating. And what we would see is pressure would go up something like what we've got here. All right. We would start out at 1 atmosphere. Let's say that's the 1 atmosphere pressure mark. And then it would just go up from there to some degree. All right, so we would take that data, plot it on the graph, and then we would ask ourselves, okay, is this a null? And no, this is not a null. We've clearly got a pattern here. And then we could begin trying to mathematically decipher the pattern. So let's do that. Mathematically speaking, what we've got here, if you this is the equation that would describe it. It would be, oops. Pressure is equal to K T. All right, that would be the most general form of this equation. And let's kind of look at what this formula is saying. Now, I would not expect you to know that formula. I'm telling you that's what the formula would be, something like that. And what I want you to do is then be able to learn why that formula is the way it is. So based on the lesson that we had during Boyle's law, we see that this is a direct relationship between pressure and temperature. As pressure goes up, temperature goes up. And I think that makes sense when you look at the data. We start with the low temperature, and we're at the lowest pressure. But then as the temperature is going up, notice the pressure is also going up. Now, the K is there as a correction factor, because if the K wasn't there, what you would have is pressure equal temperature, and that's clearly not the case. We have a 25 degree temperature and a 1 degree pressure. at the very beginning, the first data point, so they don't equal one another. But if you throw that K in there, that corrects the temperature so that they do equal one another. All right, so a lot of formulas have constants in them, and the constants are there to make the variables equate. Now, it's deeper than that, though, and I think you'll see how that is deeper here in a little bit. Let me clean up this. That. Now, what I'm going to tell you is you've actually seen something like that P equals KT before. Because when you were in algebra, you learned about the equation for a straight line. And we do have a straight line here. All right? That's linear. And you learned that when you have a straight line, that is y equals mx plus b. And I want you to notice how the y equals mx plus b looks compared to our p equals kt. Our equation starts with p, because what are we measuring on the y? Well, we're measuring pressure. So our pressure is the y variable. And then notice, instead of x, we have T. Well, that's because we're measuring temperature on the horizontal. Okay. Well, then what the heck is the K? The K is the slope. It's the slope of this line down here. If those dots were steeper, it would require a different constant to connect the pressures and the temperatures. And if it was shallower, it would require a different constant. So, yeah, the K is a slope. And what's missing from our P equals KT, now see, I have made a mess. There. What's missing, because P equals KT is just the most general form of the equation, we are missing the y-intercept. All right, so that would be down here, and that would be pressure initial, right? Initial pressure. So we don't. I guess we could do P of. So that would be starting to get a little bit more specific. If we threw in the actual K value, we would have to calculate the slope, and we threw that in there. We would have an equation that represented that actual data. And so then we would have our law that we could state verbally as temperature is direct to pressure at constant volume in a sealed container. And then we would have an equation that expresses the same thing mathematically according to our data. All right. So remember, this is all law discovery. This is stating the law. It's not a null. It's a pattern. Finding the pattern, writing the equation. Yeah, this is science, and science is awesome because we can make our own equations. So in all those math books that you've done through the years, and you were given an equation, well, someone came up with that equation. And where did they get the equation? Well, they probably pulled it off a graph, just like we're doing here. Sweet. All right. What I would say is this oozes and drips with chemistry goodness. Now, let's get away from the law stuff, and let's talk about the theory. All right, so let's see if I can. So scroll down a little bit here. And how would we go about kinetically explaining that line? All right. So why don't you pause the video here and then tell me, you write down what the particles are doing. What do you think the particles are doing? Why, based on the particles, is that line doing what it's supposed to do? So remember, you have changed the temperature and the pressure went up. All right. So pause, you write, then unpause, and I'll talk. Okay, so what's going on here with the particles is as you increase the temperature, those particles begin to vibrate more. And as they vibrate more, they're in a sealed, rigid container, a glass jar. They're going to smack the walls of the jar more often, and they're going to smack it harder when they do because we've increased their overall energy. And that is going to translate as more and more force on the inner surface of that jar. Since the jar is rigid, it can't get out of the way and relieve the pressure. It's not like filling a balloon. So it's just got to sit there and take it. And that means the pressure on the walls of those jars is going to get more and greater and greater and greater and greater and greater. Okay, so yeah, I think hopefully that appeals to your mind's eye and that makes sense. So let's look at what we've done. We have described the data. We've described the law. I've given you the data. You can see that it's direct. We've stated the law verbally. We developed a very general equation that would explain the data through the P equals KT plus PI, and that, what you're to connect there is, that's just Y equals MX plus B applied to this specific graph. Then we came in to being good scientists. We have got our law, we've described it, and now it's time to explain it, and we did. We explained it kinetically. Yes, that's why gases are awesome. Okay, so I'm going to stop the video here and move on to the next one.